Today we are going to lecture on representation of Boolean function. This is the third lesson in module 8. So let's first talk about what do we mean by representation of Boolean function. So the introduction is two important problems of Boolean algebra will be studied in this section. The first problem is, given the values of Boolean function, how can a Boolean expression that represents this function be found? This problem will be solved by showing that any Boolean function can be represented by Boolean sum of Boolean products of the variables and their complements. The solution of this problem shows that every Boolean function can be represented using three Boolean operators: the Boolean sum, Boolean dot, and Boolean complementation. The second problem is there a smaller set of operators that can be used to represent all the Boolean functions? We'll answer this question by showing that all Boolean functions can be represented using only one operator. Both of these problems have practical importance in circuit design. So even though we have raised the issue of answering both questions, the second question is not properly discussed in this section. So what we will do for this section, we will just go over the first problem, the issues with the first problem, and answering those issues. So let's start with sum of product expressions. So we will just start with example 1, and it says that find the Boolean expression that represent the function fxyz and gxyz, which are given in table 1. So if you know for the different inputs in the truth table, what are the outputs for f and g, is there a possibility for us to be able to create the Boolean function f and g? So the best way of answering this question is to look for those rows where the functions are taking the value 1. So if I look at the function f, then the only possible value 1 happens when I have the inputs for x is 1, so x equal to 1, y equal to 0, and z is equal to 1. And we want to know a Boolean function that will represent this truth column. So how do I understand that? Remember, one of the easiest way of understanding the truth value 1 is to look at the Boolean product. A Boolean product will take the value 1 if and only if all the inputs for the variables are 1. So what I get to say, x is already 1, z is already 1, but y is 0, so let's make it 1. How do I make it 1? I say take the complement of y, and that is 1. So what is f of x comma y comma z? Well, you can say that this is x times y bar times z. So if you take your fxyz as x times y bar times z, then it will satisfy the truth column given in table 1, and we have answered the question. So now we're going to look for a function that is going to satisfy the truth column given in table 1 under G. And again, I'm going to kind of follow the same procedure, with the exception this time I have two 1s. If you look at the row entry 2 and the row entry 6, then you will find 1. So what I have when x is 1, y is 1, and z is 0. So x equal to y equal to 1. And z is equal to 0, the truth value is 1. That's one of the situations. And I have when x is equal to 0, y is equal to 1, and z is equal to 0, the truth value is 1. So x equal to z equal to 0, y equal to 1. And again, think of your Boolean multiplications. So you want all three of them 1. X and y in the first situation is already 1. Z is 0, so I'm going to need x, y, z complement. In the second situation, x and z are 0. I need to make them 1. So we'll go ahead and take their complements. And I will keep y as itself because it is already 1. Now remember, the sum is going to be 1 of 1 and 0, or 0 and 1, and 1 and 1. So as long as 1 of x, y, z bar, or x bar, y, z bar is 1, their sum is going to be 1. That hints me to look for z, x, y, z as the sum of these Boolean products. So we'll call it x, y, z bar plus x bar y z bar. And that would answer my question at this point for the Boolean function. So if I'm looking for a Boolean function that will satisfy the same truth value as in column G, then the function must be x, y, z bar plus x bar, y, z bar. So the obvious question at this point that one can ask is this the unique way of representing a Boolean function? If you look at f, that's the unique way of representing that function. It is x, y bar, z. But now ask yourself how many Boolean operations you have used in order to express this function. Well, other than complementation, the only Boolean operation that we have used in this problem is product, which is answer to our second question that you need only one operation in order to express the Boolean function. Can we do a similar thing for example 2 or for the function g? So what I will say, let's start with what we have for g. So g for our example is x, y, z bar plus x bar, y, z bar. So what I can do, I can write it as x if I am letting the x stay outside, and writing it as z bar y by doing the commutativity of y and z bar, and then doing the same thing for the rest of the function. So I'm going to write the second function, I'm going to write it as x bar z bar y. Then I see an obvious factoring type of thing. Both of these expressions, they do have y in common, so I can now write it as x z bar plus x bar z bar times y. Now look at what we have inside the parenthesis. You can factor out the z bar now. So you will get x plus x bar times z bar, that's inside the parenthesis, and I do have y. Now what is x plus x bar? Well, x plus x bar is going to be equal to 1, that's one of the Boolean identities that we have seen, times z bar times y. So what I get, by the identity property 1 dot z bar is z bar, so I get z bar y, which I can use the commutativity one more time and we get yz bar. So what is the point? The point is the function g, even though it has that expression x y z bar plus x bar y z bar, you can eventually simplify that entire expression and make it look like y z bar using the distributivity property and other identities. And again, if you look at y z bar, then you would understand that the only Boolean operation that we need in order to express this function is the Boolean product. And hence, we have addressed our problem 2. So for the rest of the lecture, we are going to kind of omit mentioning problem 2, and we're going to keep writing problem 1. So given a set of values for a function, whether we can retrieve that function. So let's see what else we have. So this time we're going to define two things, the literals and the mean terms. A literal is a Boolean variable or its complement. A mean term of Boolean variables, x1, x2 up to xn, is a Boolean product of y1, y2, yn, where y1 is either xi or yi is the complement of xi. Hence, a mean term is a product of n literals with one literal for each variable. So example 2 is kind of going to introduce us to mean terms. So it says that find a mean term that equals 1 if x1 equal to x3 equal to 0, x2 equal to x4 equal to x5 equal to 1. So what we are expecting in this problem, because it is asking us to write a mean term, so we're looking for a product of these 5 variables. And I want to ensure for the product to be equal to 1, all these variables or their complements take the value 1. So I am not going to worry about x2, x4 and x5 because they're already 1. x1 and x3 are not 1, so take their complement, and hence the required mean term is the complement of x1 multiplied with x2 multiplied with the complement of x3 multiplied with x4 multiplied with x5. answers your question. And this entire technique is going to come back over and over when we will try to retrieve a Boolean function from a given set of values. So I'm going to go to our next topic. This is a topic of insertion and use of identity rules in order to retrieve a function in terms of sum of products of Boolean expressions. So the question tells you to find the sum of products of the expansion for the function fxyz, which is given by x plus y times z bar. So what we are trying to do, first and foremost, x plus y times z bar will invoke the distributivity, and you can distribute the z bar and get x z bar plus y z bar. Now see, in x z bar the term missing is y, and in y z bar the term missing is x, and I want to introduce these terms. So what I do instead, I use the identity law and write the missing terms place filled in with 1. So in the first term I write x1 z bar, in place of y I write 1. That doesn't change anything. And in the second term, in place of x I write 1 and I get 1 y z bar. Then I remind myself of the unit property. Every time you have 1, you can write 1 as the sum of any variable added with its complement. So for the first one, since y was missing, I rewrote 1 as y plus y bar. In the second one, since x is missing, I rewrote the 1 as x plus x bar. And then I used bunch of distributivity, and I got xyz bar plus xy bar z bar plus xyz bar plus x bar y z bar. Finally, I have identified that there are two xyz bars. And if I add two xyz bars, then by the law of idempotency, you get only one, x plus x bar, or any variable added with itself, x plus x, any variable added with itself is x, any variable multiplied with itself is also giving you back the same variable, which is called the idempotent law. What is the point? The point is, if you have xyz bar plus xyz bar, you get to say that there is exactly one xyz bar. And hence, my final expansion of the given Boolean function in terms of sum of the products is xyz bar plus xy bar z bar plus x bar y z bar. And this is the technique that we are going to practice a lot in our problem solving sessions. So I'm going to go ahead and skip these ideas for the time being and start working on problems. So the first problem is pretty simple, though I'm going to spend a little bit of time on this problem. This problem says that find a Boolean product of the Boolean variables x, y, z or their complements that has the value 1 if and only if x equal to y equal to 0 and z is equal to 1. So that's my first condition. So what I say, well, A will give rise to the fact that both x and y being equal to 0 and z being equal to 1, I want my Boolean function to take the value 1. Remember, I need all of them to be 1. So clearly, this is going to ask you to write it as x bar, y bar, z. Similarly, now you look at B. B tells you x is equal to 0, y is equal to 1, and z is equal to 0. So I need to change x and z to their complements. So x bar, y, z bar. The third one is x equal to 0, y and z are both 1. So y and z are good this time. So I need to change x to x bar and keep y and z. And the fourth one is when all three of x, y, z are 0. So x equal to y equal to z equal to 0. I need all three of them to be 1. So I need to take the complement of all three of them. So x bar, y bar, z bar. So my function that I'm looking forward to have is fxyz, which will take the value 1 when a, b, c, d are true, and only when a, b, c, d are true, is going to be represented by the sum of these Boolean products that we found for a, b, c, and d. So I will get to say this is x bar, y bar, z plus x bar, y, z bar plus x bar, y, z plus x bar, y bar, z bar. So in order to make sure that I have done this right, and also in order to practice the identity laws a little bit, what I have decided to do with this problem is simplifying this expansion and getting back to a simpler form of this function. And again, if I ask you this problem in your test or in your quiz, you don't have to do anything further. This is just for our practice of the identity laws, because starting with the next problem, we will be using them a lot. So what I generally do, I like to look at these terms and see if there are terms that I can combine together using the distributive law. So if you look at the second term and the third term together, then you will see that you can clearly factor out x bar y and get z bar plus z. Whereas if you look at the first and the fourth term, I see the similar argument of factoring out x bar y bar. So I will say x bar y bar, and I will also get z plus z bar inside. So what I get now, if you look at the first term, z bar plus z is 1, so you get x bar y times 1. Z bar plus z is again 1 in the second term, so you get x bar y bar times 1. Well, multiplying 1, identity rule tells you, doesn't change anything as much. But now I get to do what? I get to factor out x bar, and I get y plus y bar. Again, y plus y bar is 1, so I get x bar dot 1, which is x bar. So it seems like the function that we have found out could be simplified to the simple term of x bar. Now let's draw the truth table for x bar and verify ourselves whether we have arrived to the same conclusion as the question has asked us to. So I will necessarily get x, y, z. And as we have found out, x bar, so then I will say 4 ones followed by 4 zeros, and 1 1 0 0 1 1 0 0 1 0 1 0 1 0 1 0. And then I look at my x bar. So that's 0 0 0 0 1 1 1 and 1. Now remember, there are 4 different situations when we are supposed to have 1 as given in the problem. Do we agree with those 4 conditions? So let's check A. A says that your x and y both be 0 and z be equal to 1, which is this one. So we'll go ahead and say that this one satisfies the condition A. The second condition is your x is 0, z is 0, y is 1. X 0, z 0, y is 1. So this one is condition B. The third condition asks us to be x equal to 0, y equal to 1, z equal to 1. X equal to 0, y equal to 1, z equal to 1 is row 5. So this is condition C. And condition D asks you to be all zeros for x, y, z, which is clearly the 8th row. And hence, we have arrived at the same conclusion. The only 4 rows where x bar is 1 is where the given function is 1 as well. So the entire problem has described us pretty much everything that we have done in Boolean algebra so far. It helped us do a truth table. It helped us identifying the mean terms and writing a Boolean function in terms of an expansion of the sums of the Boolean products, and then simplifying it to write it using only one type of operation. If you look at this function, in this function, the only operation that you have used is a complementation. F of x, y, z is x complement.